Imagine you have two toy boxes in front of you. So let's suppose we have these two things in front of us, and each box has blue or red toys inside it. So this is red and this is blue. Let's suppose we are going to, and we're going to tell your friend which box has the color toy inside without opening the boxes. That's kind of like neural network does. So it tries to figure out how to make predictions about the things based on the input it gets. So here's the thing: when you start up a neural network, it is not very good at making predictions right away. So it needs some help getting started. So we need to give it some special numbers called weight that will help it learn. So these weights are like special keys to unlock secrets of how things work. So now there's a problem with giving natural neural network these initial weights. If they're too similar, then all toy boxes or input look the same to the neural network. It's like trying to tell your friend which box has red toy if you can't even see the color. The neural network is like will be just getting confused, and it will not able to make any good prediction. So what we do, we need to give those initial weights some randomness to them, like special kind of dice roll that way the neural network doesn't know which toy has what color of toy inside it first. This is called initializing the bits to random numbers. But wait, there is more. Sometimes if the weights are too big, and it can be hard for neural network to learn anything new. It is like trying to open the really tight lid on the jar of toys when you need some help getting it started. So that's where we use special number, usually around 0.01, to bump up the weights when they are too big. This is what we use to help neural networks start learning correctly and get better at making predictions over time. So lastly, we train our neural networks. We want them to be able to solve different problems by using different toy boxes or inputs. So if one toy box has a similar problem to another, we want that box to have these different keys so the neural network can tell them apart. And for really deep neural networks, sometimes we need to adjust the special number depending on how many layers they have. So basically, this is how it is, right? Let's write the basic neural network. This is our A1, this is our A2, 1, this is our A1, 2, and this is our y hat. And these things are symmetric for here. And we're going to have w1 equals to 0, 0, b1 equals to 0, 0, because these things are similar, right? So a1 of 1 is equal to a2 of 1, and az of 1 is equal to dz of 1. So proved by induction after two iterations, things are still same, so that's what it is. So w1, so this is our basic normal formula, right? So and then dw will be uv, then we're going to look this for larger neural network. So let's suppose this is a larger neural network where there are a lot of things here, and there are a lot of things, a lot of connections here, and yeah, that's how it works. Then it will be like w1 equals to np dot random dot rand n. We multiply this thing just to make it easier to open the lid. You guys remember the analogy, right? Then b1 equals to np dot 0 then w2 np dot random dot rand n 1 2 multiplied by 0.01, right? And b2 will be 0 here. And for tan h graph, if weights are too large, then these things are going to be big. That means z1 is equals to w1 x plus b1, and a1 equals to g1 z1. So this thing and this thing are going to be big. So that's all for this one. See you guys in the next one. Until then, keep hustling.